My name is Sean Kinney. I'm the managing editor for RCR Wireless News and Enterprise IoT Insights. In partnership with Qualcomm Technologies, I'd like to welcome you to our webinar today, which is titled Private LTE Networks Create New Opportunities for Industrial IoT. I'd like to introduce our presenter, Mehmet Yavuz, Vice President of Engineering, Qualcomm Technologies. Mehmet joined the Qualcomm corporate R&D department in 2003 as a senior engineer and contributed in areas including system design, development, standardization, and implementation for projects involving UMTS, HSPA, LTE, and VoIP over wireless. Beginning in 2010, Mehmet has led the LTE Small Cells Group and innovation initiatives in areas including self-organizing networks, neutral host services, the CBRS band, and LTE and unlicensed spectrum. Most recently, Mehmet has been leading the work on private Internet of Things networks and industrial IoT applications for LTE and 5G new radio. Digital transformation is a top priority for virtually every industry and enterprise. Supported by a reliable and robust foundation of wireless connectivity, the Internet of Things is poised to bring new levels of efficiency and sustainability to everything from manufacturers and utilities to airports, shipping and transit hubs, and even remote industrial sites like mines or oil platforms. As new innovative technologies and business cases come together with forward-looking spectrum regulatory policy, the reality of affordable private IoT networks can help propel the fourth industrial revolution. In this webinar, we're going to examine some of the technologies that can enable private LTE networks for the Internet of Things. On the spectrum side, the 3.5 gigahertz CBRS band promises a huge opportunity for new LTE spectrum. The CBRS band is currently used by the Department of Defense and non-federal satellite service providers, but the FCC is working to adopt a new spectrum sharing system to allow new users to access the valuable unlicensed spectrum. The current plan considers 3 tiers of access, including federal and non-federal incumbents, priority access licensees, and general authorized access users. This flexible model would depend on technological coordination to manage any potential interference between users. Then multi-fire, which is an LTE technology that operates solely in unlicensed spectrum, differs from LAA and LWA in that multi-fire removes the need for an anchor tenant in licensed spectrum. The idea with multi-fire is to make deploying LTE as simplistic as Wi-Fi by leveraging the unlicensed spectrum in the 5 gigahertz band. Simplicity and accessibility position a multi-fire small cell network, for instance, as a good option for enterprises looking to fully control connectivity while simultaneously providing multi-carrier support on a neutral host platform. This combination of technology that supports LTE and unlicensed and shared spectrum and the opportunity presented by CBRS sets the stage for enterprise and industrial interests to invest in private LTE networks that embolden the IoT and the digital transformation that it brings. For a more detailed discussion of these topics, I'm going to turn it over to Mehmet Yavuz, VP of Engineering for Qualcomm Technologies.
Thank you, Sean, for that nice introduction. And thanks to everyone for attending to the seminar. Today, I will talk about private LTE networks and how it creates new opportunities for industrial IoT domain. Private LTE networks are basically LTE-based small cells deployed locally in industrial premises. And they operate in either dedicated, unlicensed, or shared bands, and they enable customers to integrate a diverse set of devices such as sensors, machines, or vehicles across a wide range of applications and usage scenarios. So these networks provide reliability, service quality, security, and compliance with a single scalable wireless networking solution. And basically, they deliver LTE-like performance with Wi-Fi-like deployment simplicity. So I wanted to start the webinar by giving an overview of how Qualcomm sees the wireless connectivity solutions and as they transform the world. So basically, if you look at the past 30 years, Qualcomm has been driving the evolution of mobile technology by various inventions being at the center of technology development, connecting people. And if you look at the next 30 years, what we believe is making everything connected and more intelligent around people, including diverse set of devices, is a key aspect for Qualcomm. And here I would like to emphasize the diversity of the devices. And we are showing a few examples. You can see from sensors, the consumer products, the automotive and industrial applications such as robotics, machines, and so forth. We believe it's going to be important to provide connectivity for all these diverse set of devices. And if you look at the economic impact of IoT or Industry of Things, there are many studies and projections, and this slide shows a summary of what we believe, and there are a bunch of references that we list on the bottom. And basically, the interconnectivity will drive automation and create significant global economic value. And this impact is estimated to be around $6 to $8 trillion of economic value to the overall economy by 2025 to 2030. And this is essentially due to new business models, new revenue streams, and greater operational efficiencies that will be achieved by automation and intelligence. Here we show the expected distribution of this economic impact for different industries. You see the smart homes and offices creating significant value, and even higher economic value is expected in other industries such as health and retail. On the right, you see always autonomous cars, smart cities, which expect to bring a lot of economic value, but also significant value is expected in logistics such as ports, airports, and manufacturing, which can include factories, processing plants. So what you see in the industrial domain is basically what people call a revolution. There are different names for it, and some people call it Fourth Industrial Revolution, Industry 4.0, or Industrial Internet. And this is basically driven by big data, analytics, and automation. If you look at big industrial players, you see a shift in their mindset from selling products or devices to selling products as services or basically business outcomes. For example, this may mean instead of selling a power generator to a power plant, basically guaranteeing a certain amount of gigawatt hours of energy as outcome over a certain period. So to achieve this goal, many industrial players have invested into sensors and integrated these sensors to their machines. And a lot of investment has been going into analytic platforms for deep learning, machine learning, to analyze all the data generated by these sensors. And this idea is mainly called digital twin. There may be other names. But just to give an example, when an aircraft engine is sold, a digital twin is generated on the virtual environment, and the performance is continuously monitored via sensors, and a specific model for that engine is constantly updated. And this enables optimization and predictive maintenance and a lot of efficiencies that create lots of value for the end customer. And this is not only for machines, it applies to many places such as ports, logistic hubs, where improving the operational efficiency is critical. And last but not the least, there's a lot of automation going on in the manufacturing environment, such as factories. And this basically means in a factory to have reconfigurable floor space with full mobility. This involves not only machines, but also connected workers, mobile robotics with automated guided vehicles, and many sensors, a diverse set of devices. And if you look at all of these things, and the key aspect, as I mentioned before, is a need for robust connectivity. So on one hand, you have all these sensors and machines. On the other hand, you have very sophisticated analytics platforms, and you need a reliable way to connect these two things to each other. To go into a little bit more detail about these connectivity requirements, basically, many of the use cases, first of all, require wireless connectivity. I mentioned earlier automated guided vehicles with robotic arms. There are lots of drone applications. Connected workers are really important with handhelds and augmented reality or virtual reality. On the other hand, security is absolutely key requirement in these industries. Many times that may mean most of the data to be kept locally in the industrial premise. The end customers may not even want the data to leave their premise, and some of these analytics may need to be done on the local cloud. And another key aspect is the amount of data is huge. Of course, process control has been part of factories' processing plants for quite some time, but now what we are talking about is this big data and analytics, which require a lot of data volume to be extracted from these sensors and machines and fed to the analytic platforms. And lastly, I mentioned earlier, the connected devices vary a lot. Some examples here are like IP cameras with 4K video, handsets, or robotics with very low latency requirements. So these different diverse set of devices may have different set of requirements in terms of throughput, latency, quality of service. So here we are basically introducing the private LTE networks in this slide. And the private LTE networks are composed of small cells operating locally in the premise in dedicated spectrum or unlicensed spectrum or shared spectrum, which I will go into later. And they enable customers to integrate a diverse set of sensors, machines, and a range of applications and usage scenarios. These networks provide reliability and service quality, like industry-grade service quality, and basically a single network providing services with LTE-like performance and Wi-Fi-like deployment simplicity, as I mentioned earlier. And these deployments are local to the premise with a dedicated set of equipment, and the service is optimized for that particular industrial facility, which may be a set of devices, but still you have the ability to create different quality of service classes and to serve to the applications needed. And the good news is LTE is already available with different spectrum options. Core network can be hosted locally or in the cloud. And the self-organizing networks features for ease of deployment are already readily available. And lastly, of course, these networks can be integrated very nicely to the macro networks with mobility and so forth. So here you just, as an animation, we saw a truck moving the local facility can be seamlessly handed over to the macro network. So just to compare and contrast this private LTE network concept with more traditional public macro networks, what you see on the left side is private LTE networks are managed locally. They have dedicated equipment on the premise, such as small cells, or even a core network possibly. They provide local coverage and optimize for these local services. Public networks, more traditional macrocellular networks are managed by the service provider for a large coverage area, and typically they provide generic services such as voice and data. And as I mentioned earlier, we see them playing nicely together, but for some specific use cases, private LTE networks can really fill the need by the end customers. So in terms of why we believe LTE provides the high performance needed for these industrial IoT applications, here we are kind of listing different aspects. Maybe the first one is the capacity. So capacity means, very high data rates and throughput can be achieved, but also number of devices that can be supported is key. You can have hundreds or even thousands of devices supported by these small cells. And meanwhile, the reliability and latency requirements are kept such that different quality of service can be provided to different classes of devices. And another key aspect is coverage. What we see in LTE networks is really great coverage for both indoors and outdoors. Of course, there are some limitations in terms of transmit power for the specific band that is used, but generally there are techniques such as hybrid ARQ and other mechanisms that has been driven by the cellular industry for a long time, which brings the benefits in terms of coverage. Security is a key part of these cellular networks, of course. Both traditional SIM cards that has been used for quite some time, but more recently we have developed methods with some industrial partners and vendors in terms of using same level of security mechanisms, but without even a SIM card, with some embedded secure solutions within hardware. And as I said earlier, also a lot of data can be routed locally for privacy of the end customer. Seamless mobility is key in many applications, and within the premise with multiple small cells, seamless mobility can be achieved, but also service continuity can be achieved with mobility to the wide area network. And I also want to highlight an aspect which we hear a lot from industrial customers, where they would like to have a global standard. Instead of some proprietary implementations, there's a great need for a standard-based solution which has interoperability between different suppliers. We believe LTE and its evolution in 5G achieves that, and there's a rich ecosystem of vendors supplying different devices and network solutions. And very importantly, the LTE ecosystem is now evolving into 5G, and there are many enhanced features are being developed as part of the 5G new radio, such as mission-critical services. So these features provide a strong roadmap to even more use cases and applications down the road. Next, I want to talk about the network architecture aspects a little bit. Here in the middle, you see a local network. Here, the local network has multiple small cells or eNodeBs. And on the bottom, you see some access devices such as tablets, handhelds, or even augmented reality goggles by the mobile workers. You can have machines or IP cameras connected to this network, or you can have some low-end sensors with eMTC or NB-IoT type of technologies connecting to the private LTE network. But I also want to highlight a key aspect here. In practice, what you see is there are already legacy sensors and devices deployed in the field. Many of these devices can be wired sensors or I/O devices, or they can be BLE, Wi-Fi, or wireless HART, Zigbee-based sensors in the premise. And what we see them how we see them connected to the private IoT networks is through industrial gateways. So essentially, these gateways connect all these legacy devices, even wired or different wireless radio access technologies. And they can have the LTE module providing connectivity to the private LTE network. And there are already examples, commercial solutions of these industrial gateways in place, in use today. And we work with different partners to provide the LTE connectivity to these gateways for private LTE networks. Now, on the other side, as I mentioned many times, the data can be kept local through a local gateway, and local applications can be provided by this system. But the management plane, such as the core network, network management, device management, and also the analytics and services can be on the cloud. Or if it is preferred, these services can be carried to the local premise as more of a local cloud kind of service. So both options are available for core network and management and analytics platforms. Here, just to keep it a little bit more real, we want to show a few use cases. What we show here in this specific slide is a factory use case, and what we see is manufacturers are constantly seeking ways to improve operations, efficiencies, and capacity, but they are right now faced with limited network solutions to enable heterogeneous devices with mobility requirements. As an example here, we are showing some use cases with remote monitoring applications, with moving cranes, mobile workforce, handheld devices, and some machines even connecting to this network. There may be shipping, arrival, departure, which is kept track of with the same network. And these can all be done reliably, securely, and with the latency requirements of these different applications. Another example is hubs. As an example, at airports, we see increasing passenger traffic, and airports are seeking new ways to expedite basically airplane diagnostics and servicing so that the turnaround time is minimized. So if you have a private LTE network installed on the runway, that will enable to offload the engine data from the incoming airplane. This data could then be relayed to the relevant parties to conduct analytics and service orchestration to identify action required before the plane even arrives at the gate. This network can also support a lot of different use cases around the airplane. It can download the media for the entertainment system with the latest content. The ground crew can optimize the loading of luggage, maintenance, and refueling of the plane, and so forth. Another example is a shipping port. Here, the challenge we see in many ports is that increasing container traffic is overwhelming the port operators, ultimately congesting the distribution. Here, a private LTE network could support secure automation within the port while supporting wireless IP cameras, optical character recognition, OCR applications, remote monitoring of the equipment and the cranes and the tractors and trucks and the containers all within the port facility. And again, this is all done with a single network, not different networks running for different use cases. Similarly, as the ship arrives, the shipping logs can be uploaded from the ship to the ground operations, and all of these services can be orchestrated. And the very important aspect that comes a lot is the safety of the employees and workers. In a connected environment like this, there's a lot of safety benefits for the workers. Yet another example is remote sites. Here we show an oil platform. And what we hear is there can be multiple thousands of sensors in an oil rig. I have heard numbers of 30,000 sensors even. And today, there are very few of these sensors that are connected. But we believe if you have a reliable, good coverage network with private LTE, you can connect many of these sensors. You can also have many other different applications similar to I mentioned before. Maybe to highlight one different use case, you can have remote assistance for the operators. If a worker or operator is fixing a specific equipment, that worker can get remote assistance from a specialist in a remote location. You can have drones streaming HD video for doing inspections. And as you can imagine, these applications are applied to mines, construction sites, temporary sites, where the coverage becomes very important as well. Smart buildings is another use case. Here you see a shopping mall with different sensors, also moving platforms such as elevators that will require connectivity for safety and entertainment purposes. Of course, one can say all these devices can be connected via wired network, but that becomes costly and hard to maintain, as especially the network expands and as you want to connect more and more devices to this network. And obviously, similar examples include hotels, campuses, hospitals, public venues, as we list here. So one critical question is, how big is the market size? And we've been working with Arbor Research for quite some time for market size analysis for private LTE. And they have done a comprehensive analysis for the market size of smart systems. They started with 60 customer segment wide analysis with close to 500 device categories. And then from these 60 verticals, they identified high-value industrial segments, and they trimmed this down to 50 key segments. And here we are showing examples of those segments. What you see is discrete manufacturing, power generation, hospitals and labs, and oil and gas, both upstream, transport, and downstream, shipping ports, as I showed earlier, or transportation venues, distribution warehouses, surface or underground mining, power generation, and hybrid converting manufacturing. So these are the different verticals that were identified. And out of these 15 verticals, they further looked at the shipments of high-value device categories, which require reliability, mobility, strong potential value for the end customer. And then, as the last filter, they applied willingness to pay for network management services, such as private LTE network. And they arrived at this market estimate of around $31 billion by 2022. In terms of device numbers, this is approximately around 600 million devices that as potentially addressable, total addressable market for private LTE networks by 2022. You can find details on their website in Harbor Research. Another key question is, what spectrum will these private LTE networks be deployed? Here there are different possibilities. One possibility is spectrum dedicated by mobile network operators. This can be some unused spectrum. It becomes especially relevant when we are talking about remote sites where operators may not need the licensed spectrum for their regular broadband services. Another key spectrum option is 3.5 gigahertz shared spectrum, or called CBRS, Citizen Broadband Radio Service, that's becoming available in United States, where there's 150 megahertz of spectrum available. And the third option is the multiplier technology, as Sean mentioned in the beginning introduction. This is basically LTE-based technology operating in the 5 gigahertz unlicensed spectrum globally, as I will go into a bit more details a little later. So to explain the CBRS band a little bit more, this is 150 megahertz of shared spectrum in United States, which is being made available by FCC. There is a three-tier mechanism for sharing this spectrum. And there is a large ecosystem of companies, from operators to the vendors, working on bringing LTE technology to the 3.5 gigahertz band. It's basically called CBRS Alliance. There are now more than 50 members. And the main goal is to drive advanced LTE-based technologies in the CBRS band. The specifications are being developed by the ecosystem, and there are already multiple trials going on, and certification is in progress. We expect the deployment later this year, starting commercially. Just to explain this three-tiered shared spectrum aspect, because I believe this is kind of important and unique. There's incumbents that we show as tier 1, which includes military, navy, ship-based radars. There is fixed satellite stations or VESTs operating. But what you see is the usage is really sparse, and there are mechanisms put in place to enable other tiers, such as tier 2 and tier 3, to use the spectrum. The way it works is tier 2 is priority access licenses, or PAL. They can get licenses to spectrum by an auction, and up to 70 megahertz can be used by the PAL. And the third tier is GAA, Generalized Authorized Access, and they can use spectrum wherever it is not used by tier 1 or tier 2. And the whole 150 megahertz can be utilized by GAA under these conditions. And PAL and GAA are, as I mentioned, PAL can go up to 70 megahertz, and the rest can be used by GAA in all the places where spectrum is not used. Now, these networks are already demonstrated in 3.5. Here I'm showing two specific examples. First one is a NASCAR demo that was jointly done by collaboration between Qualcomm, Nokia, and Alphabet. Here, a virtual reality zone inside a stock car was done. This is basically part of the Richard Perry driving experience, creating a full 360 in-camera experience in real time. So this network shows high uplink data rate on the racetrack, high downlink data rate for the spectator area, very low latency between the car and the network, and seamless mobility. This car, I believe, was going in excess of 180 miles per hour, and a constant 4K 360 virtual reality video was streamed with great user experience, all happening in 3.5 gigahertz. Another example is a private LTE network that we deployed in San Diego, California, in our campus in a manufacturing factory environment. This network was demonstrated at Mobile World Congress. It shows how local control and optimization can be achieved for industrial applications. We demonstrate remote control of AGVs with low latency, seamless mobility. We also show quality of service, network reliability, what happens if one small cell goes down, how quickly all the devices switch to the other cells. Also, how can existing sensors with wireline and other technologies can be connected to this private LTE network via industrial gateways. And all of this network was connected to GE Predix Cloud. So this was a joint collaboration between Qualcomm, GE, and Nokia. And the key KPIs and remote monitoring of the whole network statistics were achieved through the GE Predix platform. The third aspect I mentioned was multifier, which is, as I mentioned earlier, LTE-based technology operating in unlicensed spectrum. It has listen before talk and CCA type of mechanisms needed for standalone operation in unlicensed band and coexistence with Wi-Fi. And it supports 5 gigahertz globally. There's a strong alliance developing the spec and the certification requirements. There are more than 25 members right now in Multifier Alliance. The certification program is expected to be completed by end of 2017. There are field trials planned in 2018, which will be followed by commercial products with commercial deployments. As I mentioned, we expect field trials early next year, but we already have significant progress this year. At Mobile World Congress in Barcelona, we demonstrated first over-the-air multifier network with mobility and handovers between small cells. This is in our test network where we have 4 multifier small cells deployed to cover our campus. And here you see in this video that we drive through this network, and there is live traffic going on. This whole operation is in 5 gigahertz, which is shared with normal Wi-Fi usage. And the handovers are seamless without any interruption. And it also, all these tests showed us the superior coverage we achieve with multifier networks. And if you're interested, you can find the full video online on our website. And as I mentioned earlier, a really key benefit of using global standards such as LTE for these private networks is the strong roadmap that is being developed towards features, specifically the 5G. So 3GPP is an international standard, as most of you are familiar with, where LTE is defined, and now 5G is a key focus area. Release 15 is being developed in terms of a new air interface, a new radio, which is called 5G NR. And 5G NR includes many advances, both in terms of existing mobile broadband applications with almost fiber-like experience, as well as new capabilities such as ultra-reliable, low-latency communications, or what is called URLLC. 5G NR will also enable access to more spectrum. First, in terms of wider spectrum usage will be enabled from sub 1 gigahertz bands to the millimeter wave band. 5G NR is designed from the start to support all spectrum types as licensed, shared, or unlicensed. And a lot of new study areas are being identified for 5G, and a few key things I want to highlight here related to private 5G networks is a study on operating NR in unlicensed spectrum has started. And then there are also study items on 5G for automation in vertical domains, and also local area network support in 5G is another recent study item. And we see a lot of activity in these private 5G networks domain now. With 5G NR, we expect even more use cases to be enabled, such as the factor of feature. Here, you can see how 5G NR with URLLC, with low latency, as low as 1 millisecond subframes, can possibly replace some of the wired Ethernet connectivity in these factories for different use cases. This becomes especially important for reconfigurable factories, which is important in this fourth industrial revolution that I mentioned. Mobile assembly, where the goods are moving and mobile robots doing the assembly with assistance from connected workers is really important. Here we show an example of a mobile robot, essentially an AGV with an robotic arm. There are multiple use cases where you need reliable, low latency communication to coordinate activities across these mobile robots. New use cases with augmented reality is a very key aspect where it may require very high speed and low latency connectivity provided by 5G. Again, what we see is a unified ecosystem and global solutions with a single network for the whole factory. Now, just to summarize all these different aspects we talked about, the first thing I want to highlight is that we see a large addressable market with many verticals for private LTE, where LTE is providing this high performance for a wide range of industry verticals, from factories to ports to smart buildings, a variety of verticals. Spectrum is becoming available. I mentioned operators can dedicate some spectrum, mobile network operators, but Multifier can provide a global solution in 5 gigahertz. LTE-based CBRS is already happening in 3.5 gigahertz in United States, which may drive many of the early deployments in US. And there is a strong path to private 5G NR networks, which can enable even more use cases with reconfigurable production and all these really exciting use cases I mentioned earlier. So I see that we have almost 15 minutes to the top of the hour. If you would like to learn more, we have a link at the bottom of this slide. I would like to open it for questions at this point. And thanks, Sean.
All right, thank you very much for that presentation, Mehmet. We have a lot of audience questions here, so we'll go ahead and get started. First off, one of our viewers would like to know, can devices be authenticated with private LTE networks without a SIM, which you addressed a little bit. Perhaps you could expound on that.
Yes, absolutely. Great question. It is true that the devices can be authenticated without a SIM. And we have demonstrated this capability with partners such as Nokia and Ericsson, actually. And the standardization for these mechanisms have been developed in Multifier Alliance, and it is already spec'd. And there is also work going on CBRS Alliance, which is almost complete to finalize that spec. Basically, what happens is device identity is kept securely in the device, and using that ID, the network can do subscriber certification exchange with the device using secure protocols between the end device and the network. So we believe the SIM level security can be achieved using these mechanisms. Of course, it will require a secure subsystem within the end device to store the credentials and so forth.
And another one of our viewers would like you to compare using a private LTE network versus a Wi-Fi network in an industrial IoT use case.
Yeah, this is a really good question, and we definitely see a lot of use cases that can be served with Wi-Fi, but we also see some benefits potentially with private LTE. I had that one slide that was showing some of those use cases or examples, such as capacity. You know, very large number of devices can be supported. Quality of service in terms of reliability and low latency. We see some coverage benefits with private LTE, and in also spectrum bands at 3.5 and other bands, you can have much higher transmit powers that can be enabled for outdoor deployment. And maybe one of the most important aspects is interoperability. We see a lot of proprietary or specific implementations of Wi-Fi in industrial use cases. However, what we hear from the end customers is a need for a global standard solution which has interoperability between different suppliers. So that seems like an important aspect. And last but not the least is the roadmap with the 5G features that is coming in. But as I mentioned, we see potential this private LTE and Wi-Fi working together with this industrial gateway solution, connecting all of them, all of these end devices to the same network.
All right, Mehmet, and we've got two questions here that kind of run together, and those are, will the connection of a device on a private LTE network move seamlessly to the macro network and vice versa? And then will a private LTE network interfere with the macro LTE network?
Yeah, very, very good question. So first of all, the private LTE network, we don't see interfering with the macro networks, because as I mentioned, the spectrum bands that we envision for these networks is different than the macro cellular network. Even if a macro network operator dedicates some spectrum for a certain geographic region, it will be a different channel compared to the macro network. And we definitely see mobility between these networks and the macro network. There are mechanisms already in place to enable this kind of mobility. It can be thought of, there are a few different ways to do it, but the simple way to think about this is as if there's mobility between two different operators today, or two different networks on two different bands. But they're all part of the same LTE family, so it comes native to the technology, with the technology.
And another one of our audience members asks, how do you envision a private LTE network being deployed? Would the individual company lead that, or would an LTE vendor or an LTE operator take charge?
We believe all of those are possible. It depends on the use cases. Of course, first of all, mobile network operators may choose to do so in terms of deploying some of these networks as dedicated service, and they could potentially, provide things such as network slicing and so forth. But also, separate service providers can come in and deploy these networks, maybe in coordination with the with some of the RAN vendors. We see that happening as well, providing that end-to-end connectivity service to the end customer as a managed service. And maybe for small or medium-sized enterprises or facilities, it can even be deployed by the end customer potentially, just like how Wi-Fi can be deployed, and the management and other core network services can be provided by cloud. So we need to see how the market shapes itself, but all of these things are possible, and we see a lot of activity in various areas as of now.
And another one of our viewers wants to know if a company that's using a private LTE network for industrial IoT can also leverage that same network to support their employees' smartphones.
Yeah, that's a very good question, and it's absolutely possible. That goes back to the aspect of diverse set of devices that can be supported by this network, and of course the handheld devices is definitely part of it. Now, one key aspect is how these devices are provisioned, and are they operator provided devices or open market devices? So there are some details associated with that in terms of the system selection and so forth. But what we see is a definite capability to do exactly what is said, and it makes a lot of sense once you have a good, robust coverage of LTE within the enterprise or the factory or the facility to provide that connectivity service to the employees as well.
Another audience member would like to know, can private LTE in 5 gigahertz and Wi-Fi in 5 gigahertz coexist without interfering, and is handover possible between them?
A very good question. Yes, definitely. They can coexist in 5 gigahertz. That's essentially what the multiplier technology achieves. There's already specs that have been developed and implemented and being tested, as I showed earlier in the video with the van driving in the network. So there is listen before talk type of mechanisms in place to enable coexistence on the same channel in 5 gigahertz between multiplier and Wi-Fi. But in practice, what we think is that the IT or the local, department controlling these network deployments can assign different channels to multiplier network and Wi-Fi network. So, for example, one set of devices, one network can be in Uni 1 band and the other can be in Uni 3, so that there is separate channels used in 5 gigahertz. As you know, there is more than 400 megahertz of spectrum in 5 gigahertz, and even if you use only Uni 1 and Uni 3, there is close to 200 megahertz of spectrum. And mobility, of course, is also possible between these two networks. Better yet, you can do the aggregation across multiplier and Wi-Fi networks. So we have those capabilities, at least from Qualcomm side, supported on our devices, and some of these technologies have already been demonstrated and in use today in other use cases such as mobile broadband.
Mehmet, how does the lower latency in private LTE compare with what we currently have from the macro network? And what's an example of a use case where that lower latency would create a real business value?
The QoS scheduler on the eNode B and also UE has that capability. Typically in the macro networks, only voice and best effort traffic classes are utilized today, but technology enables a different, even a larger set of classes for quality of service. And basically, it comes down to the scheduler within LTE network to provide priority for different classes of packets. In terms of one specific example, I was talking about the machine control or factory automation in what they call master-to-master type of connectivity within factory. The LTE type latency, maybe 20 milliseconds or less, is sufficient, and it can enable this reconfigurable factory spaces without a lot of Ethernet wires going around. Also, other use cases can include, AR, VR applications where latency is critical. These AGVs with, mobile robot arms also drive some of these low latency requirements. And if you want to go to master-slave type of factory automation, then you're talking about really 1 millisecond or less. So that's kind of Profinet Class C, and that's what we see down the road being enabled by 5G.
And one final question as we reach the end of the time allotted, Mehmet. How does multi-fire compare to Wi-Fi in terms of coverage range?
Yeah, so we see some benefit of multiplier in terms of coverage over Wi-Fi, and that basically goes to some of the physical layer differences in terms of hybrid hierarchy and so forth. On the device side, there is typically the devices can go to a little higher transmit power, and they can go to lower data rates as needed. So we see a significant increase in terms of coverage due to these mechanisms I mentioned earlier.
Well, Mehmet, thank you very much for your discussion and presentation today. And thank you very much to our audience for joining our webinar, Private LTE Networks Create New Opportunities for Industrial IoT. Just as a reminder, we will be distributing a recording of this webinar in the coming days. Thank you again.
Thank you, Sean, for managing this webinar, and thanks everyone for attending.